Alright, we need to continue and talk about a few properties of radicals because that can help us out as we simplify them. And that is something that shows up on some of these practice exams, some basic radical simplification questions. So let's talk about a few properties, a few rules. The first one's called the product rule. Okay, product means multiply, right? If I have radical A times radical B, I can think of that as just one big radical with the A times B inside. Okay, so I have that choice. I can take two smaller radicals and multiply the numbers inside together and then worry about the fact that it's a square root. Or I can use this to my advantage the other way. Maybe I've got some big number underneath the radical sign and I might want to break that up into the product of two smaller numbers. Okay, we will use that technique as we're simplifying. So it goes both ways. Okay, radical 2 times radical 5 equals radical 2 times 5 underneath the radical, or radical 10. Okay, it works with x, y's, and z's too. Radical 7 times 5, radical 7x times, radical 5y. So it's equal to everybody together, one big happy family here. Well, the 7 and the 5, I can call it 35, and then xy. Okay, if I happen to have a radical times itself, by the way, radical 7 times radical 7, well, what does that do for me? Well, it gives me a radical 49, but a radical 49 I can simplify and just call that a 7. Okay, so when I take some radical times itself, it's just like the radical disappears, and I just have the number that was underneath the radical. Another way to express this same thing is to say I take radical 7 and square it. Right? That's the same thing as taking that radical 7 times itself. That's what square means. And one of my little sayings, I got my math is fun, my fractions rule. One of my little sayings is that the squares and the square roots annihilate each other. Okay, I use the word annihilate instead of cancel or wipe each other out. I'm a nuclear engineer by background, so I like to throw that little tidbit in. The word annihilate just sounds cooler, right? So anyway, that becomes a 7. Alright, all good? Alright, products there, properties. We're going to use that, like I said, to simplify. Now, we all know that, radical 100, for example, is a nice, perfect, we call that a perfect square root because it square roots into a nice whole number. Okay, 10. Well, radical 500 is not so pretty. Okay, it's not a nice whole number. It's some decimal. However, from these properties we just talked about up here, I know hidden inside my 500 is a 100. Because 500, if I factor it, it becomes 100 times 5. So I can pull that radical 100 out separately and call it radical 100 times radical 5. And radical 100 I know is just a good old 10. So this simplifies into 10 times the square root of 5, or 10 radical 5. Okay, and that's what we're going to do in this simplification process. We're going to find hidden perfect square roots inside these larger numbers and pull them out. Okay, how about radical 75? That's really a radical 25 times 3, right? And I know 25 is a perfect square root. I usually skip this step here once we get the swing of it, and we say radical 25 is a 5 times radical 3. Okay, obviously it helps to know the first handful of perfect square roots, okay? It's the reverse of the first handful of squaring numbers. Okay, what about a radical 80? Now my knee-jerk might be, well, 10 times 8 is 80. Yep, roger that. Well, that doesn't help me though. Because a 10 is not a perfect square root, a 9 is not an 8 is not a perfect square root. That doesn't do me any good. So stop and think a minute. I need to factor that 80 in such a way that I get a perfect square root underneath the radical. So that's not going to help me. But what if I called it 16 times 5, right? 16 times 5 is 80. 16 is a perfect square root. Let's just do it in one shot here. We're going to square root that 16 out of there so it becomes a 4 out front, and then I'm left with a 5. Okay, so I got to choose my factoring wisely. The most obvious factor to me anyway, 10 times 8 is 80. That's the most obvious way to factor in 80. There's lots of different ways, of course. but that doesn't help me. I need to factor it in such a manner that I have a perfect square root hidden inside. Okay? If you can't get anywhere, what if I gave you radical 38? I said, simplify radical 38 for me. Well, I can't. I mean, I could call it 19 times 2, but 19 is prime, 2 is prime. Neither one of those is a perfect square root, so there's nothing more simple and clean than just leaving it as a radical 38. There's no way to simplify that. I could turn it into some decimal, whatever it is, but I can't simplify it as a radical the way I could with radical 80 right there. Okay? All right. Sweet. All right. I like it. How do we add and subtract, multiply, and divide these radicals? Well, I don't want to spend too much time on this because I don't think you'll have too many issues, but, we used the term combine like terms earlier. Well, now we're looking for like radicals, okay? A like radical. 7 radical 2 plus 5 radical 2. That's a like radical. Just like if I said 7x plus 5x, you would know exactly what to do. You'd put them together and call it a 12x. Well, that's what we're going to do here. We're going to put them together and call them a 12 radical 2. Okay? Like radicals. They must match, and then I simply add and subtract the coefficients. Okay, throw a little algebra under the radical there. I've got matching radical 5x's there. I've got no number out front, which we know what that means, right? There's a pretty 1 out there, so 1 minus 7 is going to be a negative 6 radical 5x. Okay? Adding and subtracting is that way. We must have the like radical, and then we can add and subtract it, okay? Now, let's be careful, because this next one here, it looks like we do not have like radicals, so my initial response would be, well, I can't simplify that because I don't have like radicals. However, 12 is not simplified. Radical 12 is not simplified. Let's work on that. I'm going to factor that 12. Now, calling it 6 times 2 doesn't do me any good, but I'm going to call it 4 times 3 because 4 is a perfect square root. Out it comes as a 2 in the front, right? And look at that. I did have like radicals after all. So now I can put those two things together and give myself a 9 radical 3. Okay, so it may appear you don't have like radicals when in fact you really do. Okay, if you simply don't have like radicals, radical 3 plus radical 5, there's nothing I can do there. It is what it is. I could turn them both into decimals and add them together, but that's it. I cannot combine these in any way, shape, or form. They're not like radicals. Okay? Multiplying, again, very similar to what we may think here. If I do something like the distributive property, for example, I'm going to take a radical 3 and distribute it across those parentheses. I'm going to get a radical 21 plus a radical 15, just like you might expect. Okay, my next step would be then to try to simplify. Is there anything I can do with a 21 or a 15? And I could play around here and try to factor, and the only way I can factor a 21 is 7 times 3. The only way I can factor a 15 is 5 times 3, other than, the individual factors themselves. And I would have to conclude that, there's nothing coming out of there that's a perfect square root, so there we go. That's all we can do. We haven't talked about multiplying binomials together yet, and we will do that in another section when we talk about polynomials. And in fact, I think I'll reserve it for there because I highly doubt you're going to have to multiply a radical together, binomial radicals together. So let me leave it at that for now. Okay. Now that I've said it, you're just dying to know what it is, aren't you? All right, let's do it. This is a different animal now. 3 plus radical 2 times 5 plus radical 2. This is called a binomial, 2 terms together, multiplied by 2 terms together. There's an acronym out there called FOIL, and maybe you've seen that at one point in your life. It stands for first, outside, inside. and last. Okay, we're going to do this more when we have just x's and y's and not necessarily radicals in there, okay? But it's the process is the same, so I guess we might as well bite the bullet and talk about it now. First, I'm going to take the first one here and the first one here. 3 times 5 is 15. The two on the outside, the far outside edges, so 3 times radical 2 is just going to be plus 3 radical 2. Pardon me, that's my email. I forgot to shut my phone down. 5, the two inside pieces, close together. 5 times radical 2 is 5 radical 2. Did I put, I made a mistake here. That's supposed to be 3 radical 2. I wrote radical 3. Let me change that. Okay? And then finally the last pieces. Radical 2, the last one here and the last one here. Radical 2 times radical 2 is radical 4. Okay, now I can clean this up though. 15, I can combine both of these because they're like radicals. These are both radical 2, so a 3 radical 2 and a 5 radical 2 becomes an 8 radical 2. And square root of 4, that's an easy one. That just turns into a nice pretty 2, so this is 17 plus 8 radical 2. Okay, the 15 and 2 go together. Okay? Another way to accomplish the same thing. Some people just don't like to bother themselves with this acronym of FOIL and all that business. But another way to treat the same thing, it's really just a more involved process of distributing. I'm going to take this 3 and distribute it across to both pieces. And then I'm going to take this radical 2 and I'm going to distribute it across to both pieces. That's it. 3 times 5 is 15. Plus 3 times radical 2 is 3 radical 2. Plus radical 2 times 5 is 5 radical 2. And radical 2 times radical 2 is radical 4. Okay, same thing. I'm going to combine my pieces in the middle. Square root of 4 is a nice pretty 2. And there we go. Okay? So that's, okay, I quite often refer to that as a FOIL process, and you may have heard that term before. Anyway, that's that. Okay? Alright, so that is basic operations with radicals. Let me do one more while we're on this topic of FOIL. It comes up again. If I have a number like this one, 2 plus radical 7 times 2 minus radical 7. Notice this is kind of a special one. It's the same numbers, a 2 and a radical 7 in both cases, but one has a plus sign in between and the other has a minus sign. Let's do this. Let's FOIL it out, as I say. 2 times 2 is 4. 2 times a negative radical 7 is negative 2 radical 7. 2 times a radical 7 is 2 radical 7. And then radical 7 times a negative radical 7 becomes a negative radical 49. Okay? Now look what happens when I simplify. These two middle pieces cancel each other away, right? Because I have a negative and a positive of the same thing. So I'm just left with 4 minus radical 49, which is a 7. 4 minus 7 is negative 3. Okay? It's kind of an identity that shows up a lot in math. And if I write it more generically, I've got some A plus B up here, A plus B, and then the same A and the same B, but I got a minus inside there. Okay, this is a famous identity, and this turns out to be A squared minus B squared. There's a little shortcut we can get to the answer. I could have just taken this A here, which is 2, and called it 2 squared minus B squared minus radical 7 squared. Well, 2 squared is 4 minus, and we learned that the square and the square root annihilate each other, right? So it's just a 7. And 4 minus 7 is negative 3. It's a nice little identity. I always tell students when we're going what I call in the forward direction, when we're doing this foiling business, just FOIL it out, simplify it, and be done with it. It's no big deal. It's when we go backwards, and we're going to go backwards in a little while in another video. We're going to do something called factoring polynomials, and one of the special forms is if I have it written this way, a squared minus b squared, we kind of have to have it memorized that turns into a plus b times a minus b. Okay, and we'll do some examples of that. Okay, but that's kind of this is the exact same thing. I just wrote it backwards, right? This is kind of one that's kind of important to remember when we get to that point. Okay, and right now we're just moving what I call in the forward direction. We're foiling it out, so it's not such a big deal. But when we go backwards in the factoring fashion, then it will be kind of important to remember. Okay. Okay. We're gonna cut that off here for now. Now we're going to kind of go almost taking a step back a little bit in terms of some of the complications of math, but I wanted to get radicals knocked out along with roots. Now we're going to go do something called order of operations, which always stands, all the way back to just regular arithmetic. You got to know your orders of operation, and then it carries through algebra and everything else. So I want to spend a little time talking about that.